This segment talks about recursive algebraic data types, things like trees, expressions, lists, and so on. If you remember, we've seen data types, and the typical example is the example of shapes. There we have two constructors, a circle constructor that takes one argument float, and a rectangle constructor that takes two floats. So the things in shape are either constructed with circle or with rectangle. So when we define a function over that type, we use pattern matching to select between those two alternatives. And then when we have chosen one of the alternatives, to pull out the components like the radius of the circle or the height and width of a rectangle. What we'll do in this segment is look at some examples of recursive data types, trees, canonical trees, and then we'll look in the second half of the block, we look at expressions, arithmetical expressions. And we'll also look at data types with type parameters. So that just as we've seen polymorphic functions, you can define types that are polymorphic, and we'll see some examples of those, and including standard types like maybe and list. And once we've done that, we'll also talk about a different kind of tree, a search tree, and then we'll conclude with a big case study of expressions. I guess for recursion for algebraic data types, the slogan is follow the data. And you can usually find a recursion pattern by following the recursion structure in the data. And that's particularly true for a recursive algebraic type. And its definition gives you its recursive structure, and following that structure fits in with pattern matching. So let's look at an example. We might define trees like this. We might say a tree is either an empty tree, or it's a node that consists of a left subtree, that is a tree, another tree, which is the right subtree, and a data value. So you can see here that the definition is recursive. It defines a tree in terms of a tree. And that's what we mean by recursion, using the thing you're defining as part of the definition itself. Now, there's our definition. How does that look as a data type? Well, we say data tree equals, so that's saying a tree is, and then either there's the empty value, or it's built using the node constructor, which takes a tree, an int, and a tree. So the definition of the data type pretty much mirrors my informal explanation there on the left. So there we have a definition of trees. And let's just draw some examples so it's clear what I mean here. An empty tree is just represented by a mustard coloured blob, and then a tree which has a single node carrying the value 2 and two empty subtrees you can visualize in this way. A tree here where we have a node below which there are two non-empty trees, and then at the next level down everything is empty. And then finally this example, which is the most complicated. It says at the top level there is a node, and on the left subtree is a node with the value 3 and two empty subtrees. On the right we have a node where the value is 2, and then the subtree on the left is not empty. It's itself a tree with 5 at the root and then two empty subtrees, and on the right is empty. And you can see that that's what I've drawn. Now you can see this structure is one where at any point, if we're working down the tree, at any point we're either at the an empty tree, so if you like we're at the edge of the tree, or we can make a choice to either look in the left subtree or the right subtree. So it's a binary data structure like that. And you can see that there are two instances of tree in the node. It has a left subtree and a right subtree. And so when we look at recursion, that recursion will follow the pattern of the definition. Just one more thing to say. I talked about node being a constructor. It's a function that takes a tree and entered a tree and returns a tree. So it builds a tree. It's similar to a Java constructor node, which would be a subclass of the tree class, and that would have 3 arguments. But one thing we get in Haskell is that the constructor initializes fields for us. We don't have to think about, because the fields are just the values passed to the constructor. Whereas in Java, we probably have variables inside, private variables, which are assigned values by the constructor. We don't need to do anything like that. The application of node to a tree and into the tree just is a tree itself. We don't have to do anything more. Okay, so what I'll do next is cover some definitions of functions over trees.